This is from live performance, a collaborative performance I did, where is this sort of flocking behavior to react to a live orchestra playing, and then it was sort of projected. So then it was sort of projected live. Identify some sort of behavior, and then I implement it in a computer, and then I figure out what I can do with it. So something I make a lot of use of is a computational model called cellular automata. I'm going to very briefly try to explain what that is. So let's imagine that we have a cell. It's just an entity. That's not good. I'm going to just continue anyway. Let's imagine that we have a cell. It's just an abstract entity. And
oh, you're good. You're showing the screen.
Oh, yeah? Okay. So, and that cell, before we imagine what it is, we might say that it has a state. So that the state of that cell could be either 0 or 1. And we might start a process where the state of the cell changes. So according to the rule that you see below there, if the state is 0, turn it to 1, and if it's 1, turn it to 0, and then it starts fluctuating between them. But what if we had more than one cell? What if we had 2, and each one is looking at the state of the one next to it? Then we start having a relationship and a presence of feedback. And when you start to accumulate even more cells with certain rule systems, you'd start to get very interesting behavior. Not always. Not always, but some rule systems might become quite interesting. A very good example of this is quite a large, sorry, lots of stuff going on here. Quite a large study by Stephen Wolfram, and he did a sort of rigorous survey of all possible rule systems of different ways of putting these cells in a row. And what you see here is them kind of, this is the first step and the second and the third. And when you study about cellular automata, when you start reading about it, you'd find this quite often. Let's look at a different rule system. This is the rule system that we see here on the left. It's quite a bit more complex, but still very, it's not long. It's not a complicated formula. I won't kind of recite it here, but it leads to this behavior. And it may not seem like much, but if you zoom out even further, you'd start to see that very particular patterns are formed when you run this rule system, when you let the cells look at their own neighbors and then decide on which color they should have. And that type of phenomena, these sort of structures, you might call them emergent structures because they emerge from the rules of the system. And nowhere in the program have I defined this behavior. It just happens from this very simple rule system. So again, this is a very common algorithm called the game of life. Most people know what game of life is well long before they know what cellular automata is. Again, very famous algorithm. And another thing is you don't have to stay in black or white. You could also have gradient colors. So all possible values from 0 to 1. And then here, this is a rule system where it just averages out. And what you see is sort of the sum of all neighbors divided by 9. Again, a very simple rule system, but you might start to see how there are many more options once you start going, you increase the number of possible states. So this is called reaction diffusion. Again, quite a famous algorithm, and it simulates how 2 chemicals diffuse into one another. As you can see, there are very particular forms that you can get with this that are quite interesting. So these systems, I've kind of showed you only 3 examples, but there are actually infinitely many cellular automata programs, and most of them are not interesting. They just end up being kind of this jumble of colors, but some are actually more interesting than others. And in I guess 70 years of research that we've done about this, you're almost likely to only encounter these three algorithms. Those are sort of, they became this canonical examples of cellular automata. But my question is, where are all the other ones? Why aren't we exploring them? There are tons of more behaviors out there. How can we find them? I'm sure there are interesting ones out there. So this is what I'm doing, sort of. Time will tell if that was the right decision or not, but I decided to do a PhD on this. And so I'm going to show you a bit about a bit from my work in that. So my process goes something like this. I would start with a known algorithm, what we've seen before, Conway's Game of Life. And what I would do is, what I basically did is I created this sort of, I guess you would call it a functional programming language. I can translate it from a general purpose programming language into this sort of algebraic expression. And it would look like this in my programming environment. And the nice thing about it is that when you translate programs to look like this, you can start modifying every detail about them, and they still apply, but then you start getting new behavior. And this is, I'm sort of hypothesizing that this is an interesting way to come up with novel behaviors. So this is an example of one of the first algorithms that I found. And as you can see, well, I'll give you a second to just look at it. But when I first saw this, I was mesmerized. This is 3 lines of code, and in nowhere, obviously, have I defined these structures, but they start forming into this, I guess, city of phenomena with very nuanced behavior and repetitive cycles of boxes going from one side to the other, and these pipelines where white pixels go through, and all of this from just a ridiculously small line of code. And so I basically, this is what I do. Again, not as a scientist, this is technically useless, or as of now, all of that stuff is useless. But as an artist, I get to just enjoy it and maybe apply it in an artistic context. And along the way, I've tried various ways of exploration. This is an example of trying to simulate, this is an attempt to produce a visual programming language. So, this bit of interface you see here is basically the same thing as the algebraic expression. And it's just it's a very simple mathematical formula. You may not know all of the operators, but it's just mathematical operations. And instead of using numbers, I'm doing mathematical operations on color. And again, remember, what you're seeing is each pixel being affected by its neighborhood and deciding on what sort of color it should be next. That's it. That's all we're seeing. And there are next steps to this. When you talk about exploration, you can start to think of how can I see, this is, I guess, akin to vast fields of cellular automata programs. Each rectangle here is a different program, slightly different to the one next to it. And what you're actually seeing is that when I move the mouse, I'm also slightly modifying these programs. And I get to just wander in this endless, very epileptic landscape of emergent behavior. And after doing this doing this research for something like 5 years, I've uncovered a fair amount of interesting algorithms, you might call them, interesting to me at least, and behaviors that I think, I don't know, I can't tell you now why I think this is worth studying, but I'm kind of sure it is. This is the sort of conviction that you might find artists be very involved in, but they don't know why they did something until later in their lives. So I'm sort of assuming this is the stage that I'm in now. I have very little answers about these things, but quite a lot of interesting questions, and somehow the ability to produce tools that would that allow me to do these explorations. This is another interesting experiment that I did, slightly more compound, because I've created these algorithms as expressions, as algebraic expressions. I can also treat them as if they were like a DNA structure. And what you're seeing is a genetic algorithm where I'm letting them evolve on, from one generation to the other. And at each iteration, at each generation, I'm actually selecting, it's probably hard to see, but I'm sort of hovering over the ones that I find interesting. And pretty soon you'll see a new generation formed from all these, from kind of mixing them into one another and giving them mutations. And this is an interesting way to explore different algorithms because it's open-ended. There's an infinite number of algorithms, and just like a naturally occurring process, here there's another generation coming. Yeah. So this is a new generation, and all of the members of it are just kind of crossbred from the previous ones that I've selected. So again, this is a way to navigate in this unbelievably large landscape of possible behaviors. And who knows what else is out there? No one knows. And this space is filled almost entirely with random nonsense junk. But there are also, there must be pockets of interesting behaviors that no one has ever seen before because they don't happen to be physically possible. So again, as I'm sure you can see, if you can see my face, I'm very haunted by these questions. All right, so I guess the end goal for now is to start doing, like establishing an archive, sort of like a database of cellular automata algorithms. And this is what I'm mostly involved in right now. I'm just convinced that there are interesting behaviors, and I just set out to explore, collect them, maybe perform taxonomies, maybe use, I don't know, advanced methods like machine learning to explore them and to find interesting ones later on. Okay, I'll show you, but this is a program I did for live performance. It actually uses several layers of cellular automata that I was able to modify in real time, and it manipulates an image coming from a microscope, and all of that is also sound reactive. And so this was incorporated in a live performance I did in collaboration with Musica Nova Ensemble in this year's Print Screen Festival. So I'll show a bit of this. You should be able to hear it. If not, I apologize. No, no. Be recorded. Sorry, everyone. It's sound reactive. So, yeah, I guess creative uses of this. All right. So that was that. How are we with time, Daphna? How are we with time?
We have a few minutes
Okay.
extra. I mean, it's over.
Yeah. Okay. So we have a little bit of extra time. I'm going to show you two things. One is I'll do a short demo of just a few algorithms that I have lying around here. Let's see. So this is one. Just to show you that this is, so this is running in the browser. And what you see here is this is the algorithm controlling this particular behavior. You could also sort of play around with the mouse. And the way I came up with this one, no, not you. That's embarrassing. Okay. So again, I sort of took an existing algorithm and charted many variations of it. And some of them I found interesting. For instance, this one could be quite interesting. Some of them, you see here. And then you start locating them and you come up with the interesting ones. So let's see if I can find, let's do this one. So as you can see, all happening live. So these behaviors, these are called gliders, quite similar to the ones we've seen in Game of Life, but because this is continuous state and full color cellular automata, then you'd get the emergence of much more complex structures, all these processes going back and forth. And again, this is still quite a simple program. I wonder what would happen if you start compounding more and more behaviors, and what are the limits of how complex or how interesting these behaviors can get. No one actually knows. This is really uncharted waters. 5 minutes? Okay.
Questions, yeah.
And questions?
And a little bit questions, like
So 5 questions in the 5 minutes? No.
5
Okay.
minutes, then the-
All right. Cool. So I will show you a different approach, just so that I don't only talk about cellular automata. This is a work in progress, just a different algorithm that I've been attempting. I won't talk too much about it. I'll just kind of let you simmer in it. This is a system, sort of. I don't know if I should get too far into it, but this behavior is not so much like flocking. It's much more simple than that. But this is one of the first implementations of it. And if you can see this thing, again, never programmed explicitly. This is also a very short program, maybe like 10 lines of code or something. And just with the rule systems of this world, very interesting things start to emerge. They are almost, they almost seem to have their own desires. And in different adaptations of this program, you'd start to get very interesting and nuanced behavior. Again, this is not really a simulation of any particular organism. It's just dots and lines. But they start to form these very nuanced structures. And this is the funny thing about this program. It takes it a while to evolve. It starts out being just a grid of dots. And there were like a couple of months way back when I developed this algorithm where I'd have to kind of open the program, go to bed, and then I'd wake up at morning and see what sort of what I got each time with slightly different parameters. And you get to see very interesting approaches, very interesting tactics for motion. I won't get too far into it, but there are a lot of things here that are quite a diverse array of approaches. This is a time lapse of how a dense region sort of gets these organisms start to kind of form and then they run off. Very interesting behavior, almost like looking into a microscope, but again, not a simulation of anything, just a particular way in which dots and lines can connect with one another. This is we're getting very bad frame rate here. Again, apologies. This is in certain aspects they become these mega clusters. There should even be. So this one is a time lapse of how 2 mega clusters sort of find one another, and then they. You can apply a very biological metaphor here. I'm not going to. Okay. So that was sort of a quick glance of some of the stuff that I'm interested in. If anyone has any questions, first of all here or later from the Zoom, and just cut me off whenever.
That you are like kind of developing library or database kind of pattern.
Yeah.
And you share the link to GitHub or later you share the or you don't do it.
Well, it's happening very soon, but it's not live yet. It should be. The goal is to make it more like GLSL Sandbox, like a collaborative place where everyone can log in and just explore. And the idea is that you'd get to name one. Just like thinking of how astronomers, when telescopes started becoming, so the first people with telescopes got to name all the stars. So the idea is to let everyone on the web just.
You are into like making open source.
Absolutely. And I'm inviting anyone to contact me. This is going to be a collaborative project. So everyone here and elsewhere, I'd be happy to find equally minded people that want to collaborate and help me explore, because it's a lot of work. Yeah.
Can you define your research in terms of the space and time?
What do you mean space and time?
Like we're seeing we call them patterns that they're 2-dimensional.
Yeah.
Is there a 3-dimensional
Okay.
aspect of it?
Yeah.
And you think about how you define time, which is
Yeah.
we were talking about seeing the development of the movement over the night.
Yeah.
So
Okay. So first of all, I think it's interesting because cellular automata. The question was just for the Zoom. How does this all relate in regards to space and time? If you look at something like this, so cellular automata is quite interesting. It's a discrete model. You're dealing with discrete cells and you're dealing with discrete time steps. So the concept of time is just a transition of all cells from their own state to the next one. This is happening 60 times a second, but it doesn't share our concept with time. If you have a fast enough computer, you can make it go faster. And I think it's the same thing with space. These things are abstract. They don't have physical properties. And I think part of my approach is because we've been so focused on simulating physical properties, because, let's face it, most of this stuff is done by scientists for scientists. And what scientists are mostly concerned of is, understanding our physical world. And I think it kind of promotes a bias. And maybe if we start saying, never mind physicality, never mind 3 dimensions, 2 dimensions is fine. Let's just explore this space without trying to think of our perception of time and our perception of physicality or matter. And let's just look at them as abstract structures. So my general approach would be to try and stay away from it for a second, not because I don't like it, but because I think it's maybe hindering us. It's kind of pulling us towards all the stuff that we already know. And maybe there's this kind of vast ocean of flat, abstract things that no one is looking at. So I'm very much into trying to look at, what else is there? This idea of 2 minutes. Cool. So that's kind of my approach, but I'm not married to it. This is just, this type of research I think can benefit from this approach. Other stuff that I do definitely are more simulation oriented. More questions, maybe from Zoom? Okay, maybe not from Zoom. Or we could just, yeah.
Everything you've shown is amazing.
Thank you.
But I wanted to ask about the last one. So we've seen a video.
Yeah.
Is it possible to run it or manipulate it in real time, or is it
This one?
computational intense?
No, you're not seeing it. Which one?
The last one with the clusters melting together.
Oh yeah, it's real-time software. All the stuff that I do is real-time software. Yeah, it's actually very not computational intense. It's linear, because I won't get into it, but we can talk about this. It's actually a linear algorithm. You can see what you saw there is like hundreds of thousands of nodes operating in real time, because they don't actually need to look at all the other ones. So it's linear computation, but it has a different problem which I've never been able to solve. So